frame?
We're recording.
Okay. Alright, problem 714. It's a thick concrete slab, 50 by 60 centimeters. It's placed with reference to a detector and a source illustrated in figure 7.1. I'll just attempt to draw this. I don't know how good I can. Okay, so we have source, and we have this concrete slab, and it's bouncing off, and it's not just a straight reflection, it goes down and then angles in this direction as well. So ignore air, and there's no scattering surfaces other than this under the concrete slab. So estimate the ambient dose rate at the detector for the following cases: a 2 gigabecquerel source emitting 1 2 MeV photons per transformation, and a 1 gigabecquerel source emitting 2 1 MeV photons per transformation. You make the approximation at the reflecting slabs of infinitesimal area, and if you do so, justify the approximation. So let's just say this is delta A. For simplicity, use the two-parameter Chilton-Huddleston albedo approximation. So the reason we can justify this is because the surface of the detector is smaller than or reasonably smaller than the distances. So it's going to be an approximation. It's not going to be exact. And there's some common data here. Let's call this theta naught. Let's call this theta. Let's call this psi. So we have theta naught equals 27 degrees, theta is equal to 61 degrees, and psi is equal to 30 degrees. We also have, let's call this R1. R1 is equal to 300 centimeters. R2 is equal to 500 centimeters. And our delta A has an area of 3,000 centimeters squared. So the reflected dose rate is given by equation 739. This isn't the exact equation that's in the book. So there's some other stuff going on here, but it's given by, this is what we're doing, the ambient dose equivalent, ambient dose rate. So we have a source, point source, the response function. We're going to have some area, cosine theta naught, and we're going to have our albedo, which is going to be a function of the energy and all three angles, all over 4 pi r1 squared, r2 squared. So the Chilton-Huddleston approximation will give us our albedo. this is in the book. This equation, it's in the book under the section called the Chilton-Huddleston approximation. C E naught times 10 to the 26 sigma over Z plus C prime E naught all over 1 plus cosine theta naught over cosine theta. And this is the differential scattering cross section, and that's given by an equation in that section. 1/2 r squared q squared 1 plus q squared minus q 1 minus cosine theta s, where it just keeps on going. Where q is equal to e prime over e, and where e prime can be found by Compton scattering. And our scattering angle, we have to do some geometric manipulation here. Is cosine theta s is going to be equal to sine theta naught sine theta cosine psi minus cosine theta naught cosine theta. And we get that this cosine theta s is approximately equal to negative 0.08809. And so that means that theta s is approximately 95.05 degrees.
I'm sorry, Brian, where are these in the book?
What's in the book?
These equations?
All of these?
Yeah.
This one, I looked for that in the book, I actually couldn't find it. But I'm sure it talks in the book somewhere about how you find a dose using an albedo.
Okay.
I'm not 100% positive where that's pulled from. Yeah, like, equation 745 is close to that. (746) is close to that. So I'm sure it has some simplified version somewhere that it refers to.
And what did you say was 739 earlier?
Yeah, that's what it says in the notes, but it's using 739 and some other equations pulled together to get this. But this albedo equation is given in the book underneath the Chilton-Huddleston formula, and it gives you, and you can find this differential scattering angle sigma CE over Z. You can find that somewhere in the book.
Equation 754.
Okay, yeah. And I can't find my homework from last year on this assignment, so that's why I can't give you exact references. But they're in there. And if you can't find them in the book, you can just say reference review section. You gave us the equation. Just make sure all units work out and everything. So for the first one, for the first case for A,
The alpha is also in Shields-Uville.
yeah. Well, this is using an approximation.
Yeah, but I'm saying the approximation should be Shields-Uville.
Oh, okay.
So if you don't want to go through all the math, just look it up.
A, we have a 2 gigabecquerel source, 2 MeV photon per transform. In B, we have a 1 gigabecquerel source with 1 MeV photons per transformation. So, for A, we get that our source strength is equal to 2 times 10 to the 9 per second. And we can get our response function from Shield-Util or from the back of the book, and it's about 8.6 times 10 to the negative 12 sieverts centimeters squared. And from the Compton formula, U prime is going to be 0.380 MeV. You do some more calculations, you can get that sigma CE is equal to 0.12 times 10 to the negative 26 centimeters squared per steradian. And finally, that the differential albedo is 0.00739. So that your final answer for A, you can get that H is equal to 1.2 times 10 to the negative 12 sieverts per second. Part B is exactly the same, except it's just different numbers. So your source strength now is 2 times 10. 1 times 10.
Yeah, wouldn't it be 1 times 10 to the 9? You have a 1 gigabecquerel source.
But it emits 2 per transformation, yeah.
Oh,
2 1 in WBC.
okay. And so you just take 2 times.
Almost got you. So it's actually it's the same source strength, except one of them this is different energy than that. So the response function is going to be different. Response function is 5.2 times 10 to the negative 12 sievert centimeter squared. E prime's the same. No, I lied. E prime's different. E prime is 0.320 MeV. Right, that's so you guys can read it. And the albedo is slightly different also. It's different energy. 0.0122 is the albedo. And you, your sigma CE calculates down to 0.318 times 10 to the negative 26 centimeters squared per steradian. And finally, you get that your dose equivalent is 1.2 times 10 to the negative 12 sieverts per second. Does anybody have any other questions in this problem? I might not be a ton of help on this problem.
Seems pretty straightforward, just plug the stuff in.
Yeah, but the question of where those come from, I'm not entirely positive on those. They're in there somewhere.
Yeah, we found a couple of them.
Okay, good.
pages.
Yeah, I write those down up here. Which ones did you find?
You found two of them.
Well, the one he gave us is, it looks like it's similar to the one on 252.
What do you mean?
It's like, well, there's several, 7.7.
Oh, yeah, say. One of them was equation 7.54. It's on page 240, bottom of 240.
Yeah. Could be getting into this ducks, that's not that. Yeah.
But it's a third case.
Well, that's next. What's up?
Oh, I meant on 252.